Tonight, we are going to visit the most promising place in the solar system to find life beyond Earth. Not Mars, though Mars has captivated our imaginations for over a century. Not Titan, though Titan's methane seas and organic chemistry are extraordinary. The most promising place is a moon of Jupiter. A moon slightly smaller than our own moon, covered in a shell of ice so smooth and so bright that it reflects nearly all the sunlight that hits it. One of the smoothest, cleanest surfaces in the entire solar system. A world with almost no craters, almost no mountains, almost no features at all when seen from a distance. Just a pale, fractured sphere of ice crisscrossed with reddish-brown lines that look from orbit like veins on a bloodshot eye. Europa. Beneath that ice, beneath a frozen shell that may be 20 to 30 kilometers thick, a barrier taller than 3 Mount Everests stacked end to end, lies an ocean, a liquid, saltwater ocean. An ocean that contains more water than all of Earth's oceans combined, possibly 2 to 3 times more. An ocean that has existed for billions of years, kept liquid not by sunlight, which barely reaches this far from the sun, but by the relentless gravitational kneading of Jupiter, whose tidal forces squeeze and flex Europa's interior, generating enough heat to keep the water liquid in the permanent darkness beneath the ice. And here is what makes Europa extraordinary tonight. In 2026, new studies reanalyzed the interior dynamics of Europa and reached a conclusion that sent a chill through the astrobiology community. Europa's seafloor may be geologically quiet, not the roaring, vent-studded, mineral-rich ocean floor that scientists had hoped for. The kind of active seafloor that supports thriving ecosystems on Earth. But a calm, still, possibly lifeless expanse of rock, with little or no volcanic activity, little or no hydrothermal circulation, and little or no chemical energy for potential organisms to feed on. But, and this is the twist that makes this story so compelling, another study published the same month proposed that life on Europa would not need hydrothermal vents at all. Nutrients could reach the ocean from above, carried down through the ice shell by sinking pockets of salty brine, shuttling oxygen and other oxidants from the radiation-blasted surface into the dark ocean below. Europa might not need a hot seafloor. It might feed itself from the top down. Tonight, we are going to walk through 7 shocking discoveries about Europa and the ocean worlds of our solar system. Worlds where liquid water hides beneath shells of ice, heated by forces that have nothing to do with sunlight. We will begin with the night in January 1610, when a man in Padua pointed a telescope at Jupiter and changed everything. We will follow the story of Europa's discovery through centuries of speculation, through the space age, through the Voyager flybys and the Galileo mission that first revealed Europa's cracked and youthful surface. We will dive beneath the ice into the hidden ocean and confront the evidence, the tantalizing, maddening, incomplete evidence for and against life. We will meet Europa's siblings, Ganymede, the largest moon in the solar system, which hides its own ocean beneath its cratered exterior, and Callisto, the most battered world in the solar system, which may harbor an ocean of its own despite showing no signs of geological activity whatsoever. We will follow NASA's Europa Clipper spacecraft, the largest interplanetary spacecraft ever built, currently crossing the solar system on a 6-year journey to Jupiter, and learn how it will search for signs of life without ever landing on the surface. And we will step back and realize something remarkable. The solar system is full of oceans, not on the surfaces of planets where we expected to find them, but hidden beneath ice in the cold outer reaches where no one thought to look. By the end of tonight, you are going to understand why the search for life in our solar system has shifted from the red deserts of Mars to the frozen moons of the outer planets, and why the answer to the question, "Are we alone?" may be hiding in the darkest, coldest places we know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The story of Europa begins with a telescope, a notebook, and a night that rewrote astronomy. On the evening of January 7, 1610, Galileo Galilei, a 45-year-old professor of mathematics at the University of Padua in the Republic of Venice, pointed a small telescope toward Jupiter. The telescope was crude by modern standards, about 20 times magnification, with a narrow field of view and imperfect lenses that produced blurry, distorted images. But it was enough. Through the eyepiece, Galileo saw something that no human being had ever seen before. 3 small, bright points of light arranged in a line near Jupiter, 2 to the east and 1 to the west. He assumed they were stars, fixed, background stars that happened to lie near Jupiter in the sky. He noted their positions in his notebook and moved on. The next night, he looked again. The 3 points had moved. They were now all on the west side of Jupiter. Galileo was puzzled. Stars do not move. He waited for the next clear night. The points had moved again. Over the following week, Galileo tracked their positions obsessively, night after night, recording each observation with meticulous care. By January 15, he had identified 4 separate points of light, all moving in a regular pattern around Jupiter, sometimes appearing on one side, sometimes on the other, sometimes hidden behind or in front of the planet itself. The conclusion was inescapable. These were not stars, they were moons, worlds orbiting Jupiter, just as our moon orbits Earth. Galileo had discovered the first moons ever seen beyond our own. He called them the Medicean stars, in honor of his patron Cosimo de' Medici. He published his findings in a small book called Sidereus Nuncius, Starry Messenger, in March 1610, and copies spread across Europe with extraordinary speed. Within weeks, astronomers across the continent were confirming his observations. The German astronomer Simon Marius claimed to have observed the moons independently, and it was Marius who proposed the names we use today: Io, Europa, Ganymede, and Callisto, drawn from the myths of Zeus, the Greek counterpart of Jupiter. Each name belongs to a figure loved or pursued by the king of the gods. Europa was a Phoenician princess, daughter of the king of Tyre, whose beauty attracted Zeus. According to the myth, Zeus transformed himself into a magnificent white bull to approach her, and when Europa climbed onto his back, he carried her across the sea to Crete. It is a story about being carried to unknown shores. A fitting name, perhaps, for a moon that may carry us to the most profound discovery in the history of science. This discovery was revolutionary in ways that went far beyond astronomy. In 1610, the dominant model of the universe, the model taught in every university, endorsed by the Catholic Church, accepted by nearly every scholar in Europe, was the Ptolemaic system, which placed Earth at the center of the cosmos. Everything, the sun, the moon, the planets, the stars, orbited Earth. Galileo's moons shattered this model. Here were 4 bodies clearly orbiting Jupiter, not Earth. If Jupiter could have its own moons, then Earth was not the center of everything. The universe was not arranged for our benefit. Other worlds had their own systems, their own satellites, their own gravitational centers. It would take decades for the full implications to sink in. Galileo would face the Inquisition in 1633, be found vehemently suspect of heresy, and be sentenced to house arrest for the remainder of his life. A life that lasted until 1642, when he died at his villa in Arcitri, near Florence, blind and elderly, but unbroken. The moons he had discovered continued their orbits around Jupiter, indifferent to the politics of Earth. And the controversy their discovery had ignited, the slow, painful transition from a geocentric to a heliocentric understanding of the cosmos, continued long after his death. There is a thread that connects Galileo's observations in 1610 to the mission of Europa Clipper in 2024. Galileo saw 4 points of light near Jupiter and realized they were worlds. 4 centuries later, we are sending a spacecraft to one of those worlds because we have reason to believe it harbors an ocean and possibly life. The chain of discovery is unbroken. Telescope to spacecraft, curiosity to engineering, observation to exploration. What Galileo began with a crude lens and a notebook, we are continuing with a billion-dollar spacecraft and instruments that can detect individual molecules. The scale has changed, the impulse has not. 4 centuries after Galileo's discovery, the Galilean moons remained points of light. Small, bright dots visible through telescopes. Interesting primarily for their orbital mechanics. Astronomers tracked their movements with increasing precision, using them as timekeeping devices and navigational aids. In 1676, the Danish astronomer Ole Rømer used the timing of Io's eclipses behind Jupiter to make the first measurement of the speed of light, noticing that the eclipses came earlier when Earth was closer to Jupiter and later when Earth was farther away, and correctly attributing the difference to the finite travel time of light across the changing distance. The moons of Jupiter helped us understand light itself. But what the moons were, what they were made of, what their surfaces looked like, whether they had atmospheres or oceans or geological activity, remained unknown until the space age. For over 360 years, Europa was just a dot, a bright, intriguing, unknowable dot. Of the 4 Galilean moons, Europa is the second closest to Jupiter, orbiting at an average distance of about 671,000 kilometers, roughly 1.7 times the distance from Earth to our moon. It completes one orbit every 3.5 Earth days, locked in a gravitational dance with Io and Ganymede called the Laplace resonance. For every one orbit Ganymede completes, Europa completes exactly 2 and Io completes exactly 4. This resonance is not a coincidence. It is maintained by the mutual gravitational interactions between the 3 moons, and it has profound consequences for Europa's interior, as we will see. The Laplace resonance is one of the most elegant structures in celestial mechanics. It was first described mathematically by Pierre-Simon Laplace in the late 18th century, and it works like this. Every time Io completes 2 orbits around Jupiter, Europa completes exactly 1. And every time Europa completes 2 orbits, Ganymede completes 1. The 3 moons are locked in a 4:2:1 ratio, a relationship maintained by their mutual gravitational interactions across millions of years. Each moon tugs on the others at regular intervals, nudging their orbits and preventing them from drifting into circular paths. This is crucial, because if Europa's orbit were perfectly circular, there would be no tidal variation. The moon would experience the same gravitational pull from Jupiter at every point in its orbit, and there would be no flexing, no friction, no heat. It is the slight eccentricity of the orbit, the gentle ellipse maintained by the resonance, that makes all the difference. Think of it this way. When Europa is at the closest point in its orbit, a point called perigeo, Jupiter's gravity is slightly stronger, and the Moon is squeezed into a more elongated shape. When Europa moves to the farthest point in its orbit, apogeo, the gravitational pull weakens, and the Moon relaxes slightly. This squeezing and relaxing happens every 3.5 days, over and over, for billions of years. The deformation is tiny, perhaps 30 meters of tidal bulge on a world over 3,000 kilometers across. But it is enough. The internal friction generated by this constant flexing heats Europa's interior in the same way that repeatedly bending a paperclip heats the metal at the bend. It is this gentle, persistent, rhythmic heating that keeps Europa's ocean liquid. The resonance also means that the three moons never align on the same side of Jupiter. Their conjunctions are always evenly spaced, preventing any one alignment from becoming too strong and disrupting the system. It is a self-regulating mechanism, a gravitational clockwork that has been ticking for billions of years, keeping the orbits eccentric, keeping the tidal heating active, and keeping Europa's ocean from freezing solid. Europa is small, about 3,121 kilometers in diameter, slightly smaller than Earth's moon. Its mass is about 65% of the moon's mass. If you placed Europa next to Earth, it would look like a large marble beside a basketball. It is, by planetary standards, a modest world, unremarkable in size, unremarkable in mass, unremarkable in nearly every way except one. Its surface. Europa's surface is unlike anything else in the solar system. It is made almost entirely of water ice, bright, clean, reflective ice that gives the moon an albedo of about 64%, meaning it reflects nearly 2/3 of the sunlight that hits it. The surface is extraordinarily smooth. There are almost no large impact craters, no towering mountains, no deep basins. The tallest features on Europa are only a few hundred meters high. If Europa were shrunk to the size of a billiard ball, it would be smoother than the billiard ball. The absence of craters is the key. In the solar system, craters are a clock. Every solid surface in the solar system is bombarded by meteoroids and comets over time, accumulating craters at a roughly known rate. A surface with many craters is old. It has been exposed to bombardment for billions of years. A surface with few craters is young. It has been resurfaced recently, erasing the record of past impacts. Europa's surface has remarkably few craters, suggesting that it is very young, perhaps only 40 to 90 million years old, constantly renewed by geological processes that erase craters as fast as they form. But what kind of geological processes can resurface an icy moon? The answer lies in the lines. Europa's surface is covered with an intricate network of linear features, long crisscrossing ridges, grooves, and bands that stretch for hundreds or thousands of kilometers across the ice. These features are called lineae, and they are Europa's most distinctive visual characteristic. Some are double ridges, parallel raised lines with a trough between them, like railroad tracks etched into the ice. Some are dark bands, wide, smooth lanes of darker material that appear to have formed where the ice shell pulled apart like a crack in a frozen lake that fills with slush from below. Some are chaotic regions, areas where the ice has been broken into jumbled blocks, rotated, and refrozen in new orientations, like a jigsaw puzzle that has been shaken and reassembled incorrectly. Scientists call these regions chaos terrain. The lineae tell a story. They tell us that Europa's ice shell is not static. It moves, it cracks, it pulls apart, it shifts. The double ridges may form when cracks in the ice open and close repeatedly with the tidal cycle, squeezing warm ice or liquid water up through the crack and building up ridges on either side like toothpaste squeezed from a tube. The dark bands may form when the ice shell spreads apart, allowing warmer material from below to fill the gap, a process analogous to seafloor spreading on Earth, where tectonic plates pull apart and new crust forms at the mid-ocean ridges. The chaos terrain may form when warm ice or liquid water from below melts through or disrupts the overlying ice shell, breaking it into fragments that shift and refreeze. There is one more type of surface feature that deserves special attention. In several regions of Europa, Galileo's cameras captured areas where the ice shell appeared to have broken into large, flat-topped blocks, icebergs essentially, that had drifted apart, rotated, and refrozen in new positions. Scientists realized that they could reconstruct the original pattern by fitting the blocks back together like a jigsaw puzzle. When they did, the fit was remarkable. The blocks snapped back into place, showing that the surface had been disrupted from below. The blocks had floated freely in a liquid or slushy medium, and then the medium had refrozen, locking them in their new positions. This was the first direct visual evidence that liquid water, or at least warm, soft ice, had existed at or near the surface at some point in Europa's recent history. The chaos terrain tells a similar story, but on a larger scale. Some chaos regions cover areas hundreds of kilometers across, vast tracts of disrupted ice where the normal surface has been replaced by a jumbled mosaic of tilted blocks, smooth refrozen material, and hummocky terrain. The formation of chaos terrain may involve the melting or warming of the ice shell from below, perhaps by a rising plume of warm ice from the ocean ice boundary, or by a pocket of brine that melts its way upward through the shell. When the warm material reaches the surface, it disrupts the overlying ice, creating the chaotic landscape we observe. These features are dynamic. They are evidence of a world that is actively evolving, actively cycling material between its surface and its interior. Europa is not a static ball of ice with an ocean trapped inside. It is a system, a geological system, a chemical system, possibly a biological system, in which material moves between the ocean, the ice shell, and the surface in a continuous, if slow, cycle. All of these processes point to the same conclusion. Something is happening beneath the ice, something warm, something fluid, something that is actively reshaping Europa's surface from below. This is shocking discovery number one. There is an ocean beneath the ice, and it may contain more water than all of Earth's oceans combined. The idea that Europa might have a subsurface ocean was first proposed in the late 1970s, shortly after the Voyager spacecraft made their historic flybys of the Jupiter system. Voyager 1 flew past Jupiter in March 1979, followed by Voyager 2 in July 1979. Both spacecraft returned stunning images of Europa, images that revealed for the first time the moon's remarkably smooth, fractured surface. Scientists were immediately struck by the absence of large craters and the abundance of linear features, the cracks and ridges that we now call lineae. The surface looked young, active, dynamic, utterly unlike the ancient, heavily cratered surfaces of most airless bodies in the solar system. Scientists compared Europa to the other icy moons they had seen, Callisto's battered, crater-saturated face, Ganymede's mixture of old and young terrain, and Europa stood apart. It was the youngest-looking solid surface any spacecraft had ever photographed. Whatever was happening to Europa, it was happening now. Not billions of years ago, but in the recent geological past, possibly in the present. Shortly after the Voyager encounters, several scientists independently proposed that tidal heating could maintain liquid water beneath Europa's ice. The concept was elegant. Europa orbits Jupiter in a slightly eccentric orbit, not a perfect circle, but a gentle ellipse. This eccentricity is maintained by the Laplace resonance with Io and Ganymede, which prevents Europa's orbit from circularizing. As Europa moves closer to and farther from Jupiter during each orbit, Jupiter's enormous gravity, the most powerful gravitational field of any planet in the solar system, squeezes and stretches the Moon. This tidal flexing generates friction in Europa's interior, and friction generates heat. The calculations showed that tidal heating could generate enough energy to keep water liquid beneath the ice, creating a global ocean, insulated from the cold of space by the overlying ice shell, heated from below by the constant gravitational massage of Jupiter. It was a remarkable idea, an ocean sustained not by sunlight but by gravity. But the idea remained theoretical until the Galileo spacecraft arrived at Jupiter. The wait was long. The Voyager flybys themselves were brief but revelatory. Voyager 1, arriving first in March 1979, passed through the Jupiter system on a trajectory that favored close encounters with Io and Jupiter itself, capturing Europa at a relatively modest resolution. But even those images were enough to show something unusual, a surface that was smooth, bright, and crisscrossed with dark lines, unlike any other body the spacecraft had visited. 4 months later, Voyager 2 passed through on a trajectory that brought it closer to Europa, returning images with a resolution of about 2 kilometers per pixel, sharp enough to reveal the extraordinary complexity of the linear network, the absence of large craters, and the subtle variations in color and brightness that hinted at compositional differences across the surface. It was the Voyager 2 images that triggered the first serious scientific discussion about an ocean. The smoothness of the surface, combined with its apparent youth, demanded an explanation. Ice alone, static, frozen, inert ice, could not explain what the cameras were showing. Something beneath the surface was refreshing, renewing, and reshaping the ice on timescales of tens of millions of years. The most natural explanation was liquid water, an ocean that cracked the ice from below, filled the cracks with fresh material, and erased the craters before they could accumulate. The Voyager science team published their initial interpretations in 1979 and 1980, and the papers sparked a wave of theoretical work that would continue for decades. For nearly 2 decades after the Voyager flybys, Europa sat there, tantalizingly close in astronomical terms, impossibly far in engineering terms, waiting for a spacecraft capable of studying it in detail. Several mission concepts were proposed and cancelled. The Jupiter Icy Moons Orbiter, an ambitious nuclear-powered spacecraft, was studied extensively in the early 2000s before being cancelled due to cost and technical complexity. The Europa Orbiter concept was considered and shelved, budgets tightened, priorities shifted. Mars consumed much of NASA's attention, particularly after the discovery of evidence for ancient water on the Martian surface by the Mars exploration rovers. Europa waited. Finally, in the late 1980s, a mission took shape. NASA's Galileo spacecraft, named appropriately after the man who discovered Europa, launched on October 18, 1989, aboard the space shuttle Atlantis. The mission had a troubled beginning. The shuttle deployment went smoothly, but Galileo's high-gain antenna, the large umbrella-shaped dish designed to transmit data at high rates, failed to fully deploy. The antenna's ribs stuck together, probably because lubricant had been lost during years of storage before launch. Engineers tried everything: heating it with sunlight, cooling it in shadow, cycling the deployment motor more than 13,000 times, but the antenna never opened. Galileo would have to conduct its entire mission using a low-gain antenna that transmitted data at a rate about 10,000 times slower than planned. Instead of sending thousands of high-resolution images, Galileo would send hundreds. Every image, every spectrum, every data set had to be carefully prioritized and compressed. It was like trying to study a masterpiece painting through a keyhole. Despite this handicap, Galileo entered orbit around Jupiter on December 7, 1995, and over the next 8 years made 11 targeted flybys of Europa, approaching as close as 201 kilometers above the surface. And even with its crippled antenna, even with its limited data rate, the data it returned transformed Europa from a theoretical curiosity into the most compelling target for the search for life in the solar system. The evidence for an ocean came from multiple, independent lines of investigation. First, the surface itself, the extreme youth of the surface, the lineae, the chaos terrain, the spreading bands, all consistent with an ice shell floating on a liquid layer, cracking and moving in response to tidal stresses. Second, the magnetic field. Galileo's magnetometer detected an induced magnetic field around Europa, a field that varied in response to Jupiter's rotating magnetic field, exactly as you would expect if there were a global layer of electrically conducting fluid beneath the surface. Fresh water would not produce such a signal. Salt water would. The induced magnetic field was strong evidence for a global salty ocean. Third, the composition of the surface. Galileo's near-infrared spectrometer detected hydrated salts, magnesium sulfate and possibly sodium sulfate on Europa's surface, particularly along the lineae and in the chaos regions. These salts are consistent with ocean water that has reached the surface and evaporated, leaving behind mineral deposits, like the salt flats left behind when a lake dries up on Earth. Fourth, later observations from the Hubble Space Telescope provided tantalizing evidence for water vapor plumes erupting from Europa's surface. Initen zond oheb. Hubble detected what appeared to be plumes of water vapor rising about 200 kilometers above Europa's south polar region, similar to, though less dramatic than, the geysers of Saturn's moon Enceladus. The detections were sporadic and difficult to confirm. Sometimes the plumes appeared, sometimes they did not. But if real, they would represent direct samples of Europa's ocean being ejected into space, accessible to a passing spacecraft without the need to land or drill through the ice. And in 2019, astronomers using the Keck Observatory in Hawaii directly detected water vapor above Europa for the first time from a ground-based telescope, a measurement that confirmed that water is indeed escaping from the moon, though whether it comes from plumes, from sublimation of surface ice, or from some other process remains debated. The plume question is one of the great unresolved puzzles about Europa. If plumes are real and persistent, they would be transformative for exploration, just as the plumes of Enceladus allowed Cassini to sample that moon's ocean without landing. Plumes on Europa could allow Europa Clipper to fly through erupted ocean material and analyze it directly. The MASSPEX mass spectrometer and pseudodust analyzer are both designed with this possibility in mind. They could detect amino acids, fatty acids, and other organic molecules in plume material at extraordinarily low concentrations. But if the plumes are intermittent, small, or absent during the mission's flybys, Europa Clipper will rely on its other instruments, The radar, the cameras, the spectrometers to study the ocean indirectly through its effects on the surface and ice shell. There is also the question of what the plumes, if they exist, tell us about the ice shell. For water to erupt through 29 kilometers of solid ice, there must be pathways, fractures, faults, or conduits that connect the ocean to the surface. These pathways could be maintained by tidal flexing, which continuously opens and closes cracks in the ice, or they could be temporary, opening during periods of particularly strong tidal stress and closing again as the stress relaxes. Understanding the plume mechanism would tell us about the dynamics of the ice shell, how it cracks, how it heals, how material moves through it, and how connected the ocean is to the surface. Galileo itself met a deliberate end in September 2003, when mission controllers sent the spacecraft plunging into Jupiter's atmosphere. Like Cassini at Saturn years later, the decision was driven by planetary protection. With a dead spacecraft potentially drifting into Europa's surface, scientists could not risk contaminating the very ocean they hoped to explore. Galileo burned up in Jupiter's clouds, its atoms joining the hydrogen and helium of the giant planet, its mission complete. The picture that emerged from Galileo and subsequent observations is extraordinary. Europa has a metallic iron core, surrounded by a rocky mantle, surrounded by a layer of liquid saltwater, roughly 60 to 150 kilometers deep, far deeper than any ocean on Earth, topped by an ice shell that may be 15 to 30 kilometers thick. The total volume of liquid water may be 2 to 3 times the volume of all of Earth's oceans combined, making Europa one of the wettest places in the solar system, despite being covered in ice and bathed in temperatures of minus 160 degrees Celsius. But having an ocean is not by itself enough for life. Life, at least life as we understand it, requires 3 things: liquid water, the right chemistry, and a source of energy. Europa has the water. The question is whether it has the other 2. This is shocking discovery number 2. The ice shell is not just a barrier, it is a delivery system. For decades, scientists assumed that if life existed on Europa, it would be powered from below, by hydrothermal vents on the ocean floor, similar to the vents that support thriving ecosystems in the deep oceans of Earth. These vents would provide both chemical energy and essential minerals, creating oases of habitability in the dark ocean. The model was appealing because it mirrored what we know about the deepest, darkest ecosystems on our own planet. The black smokers and white smokers of the mid-ocean ridges, where superheated water laden with dissolved minerals erupts from the seafloor, supporting communities of organisms that have never seen sunlight and have no need of it. But in January 2026, a team of scientists at Washington University in St. Louis published a study that cast doubt on this model. Using detailed computer simulations of Europa's interior, they modeled the tidal heating within the moon's rocky mantle and concluded that the seafloor is probably geologically quiet. Unlike Earth, where tectonic plates collide and separate, driving volcanic activity along the plate boundaries, Europa's rocky interior may not have enough internal heat to drive significant volcanic or hydrothermal activity. The seafloor may be cold, still, and inert, a flat expanse of rock with little or no volcanic activity, little or no mineral-rich hot water, and little or no chemical energy for organisms to exploit. This was sobering news. If Europa's ocean has no hydrothermal vents, then the most direct analogy to Earth's deep-sea ecosystems fails. The organisms that thrive at Earth's hydrothermal vents chemolithotrophic bacteria and archaea that extract energy from the reaction between hot, mineral-rich water and dissolved chemicals, would have nothing to feed on at Europa's quiet seafloor. But the same month, another group of researchers proposed an alternative. Life on Europa might not depend on the seafloor at all. It might depend on the ceiling. Europa orbits deep within Jupiter's magnetosphere, the enormous bubble of charged particles trapped by Jupiter's magnetic field. Jupiter's magnetosphere is the largest structure in the solar system. If it were visible to the naked eye, it would appear from Earth as a disk several times the size of the full moon. Within this magnetosphere, charged particles, electrons and ions, are accelerated to tremendous energies and rain down on Europa's surface continuously, bombarding the ice with radiation. This radiation is destructive. It would kill any unprotected organism in minutes, but it is also creative. When high-energy particles strike water ice, they break apart the water molecules, producing oxygen, hydrogen peroxide, and other oxidants. Over millions of years, this radiation chemistry has produced a thin layer of oxygen and other reactive chemicals on Europa's surface, chemicals that could serve as food for organisms in the ocean below, if only they could get there. And they may be getting there. A ikin insan iki study by researchers at the University of Texas at Austin proposed that Europa's chaos terrain, those regions where the ice has been broken and jumbled, may be acting as a transport mechanism, carrying oxygen and other surface chemicals down through the ice shell and into the ocean. The model works like this. As warm ice or brine rises from below, it disrupts the surface ice, creating the chaotic, jumbled landscape. When the disruption subsides and the ice refreezes, surface material, including the radiation-produced oxidants, is trapped within the new ice and carried downward as the ice shell slowly cycles, delivering a steady supply of chemical energy to the ocean. A separate Ikazan-Saza study reinforced this idea, proposing that pockets of salty brine within the ice shell could act as conveyor belts, sinking through the ice under their own weight and carrying dissolved oxidants and nutrients from the surface to the ocean. These brine pockets, dense, salty liquid that remains unfrozen even within the ice shell, would percolate downward through the ice, delivering surface-produced chemicals to the ocean like slow-dripping IV bags of nutrient solution. If this model is correct, then Europa's ocean does not need hydrothermal vents. It feeds from the top down. Jupiter's radiation creates the food, and the ice shell delivers it. The very thing that makes Europa's surface lethal, the intense radiation, may be what makes its ocean habitable. It is a beautiful irony. The radiation that would kill you on the surface may be what sustains life beneath it. And there is a third possibility that makes the picture even more interesting. Even the 2026 study that found Europa's seafloor to be quiet acknowledged that the result is not absolute. The models involve significant uncertainties about the interior composition, the viscosity of the mantle rock, and the distribution of tidal heating. It is possible that the seafloor is quiet on average, but active in localized regions, that pockets of volcanic or hydrothermal activity exist at specific locations, perhaps where the rock is weaker or where tidal stresses are concentrated. Earth's hydrothermal vents are not uniformly distributed across the ocean floor. They are concentrated along plate boundaries and hotspots. Europa does not have plate tectonics, but it could have localized heat sources that produce hydrothermal activity in specific areas. Furthermore, a separate study published the same month noted that even a quiet seafloor interacts chemically with the ocean. Water in contact with rock dissolves minerals over time, silicates, sulfates, carbonates, producing a steady, if slow, supply of dissolved chemicals. This process, called water-rock interaction, does not require volcanic heat. It simply requires time, and Europa's ocean has had billions of years. One of the most important water-rock interactions is a process called serpentinization. When water reacts with certain iron and magnesium-rich minerals, olivine and pyroxene, common in the kind of rocky material that makes up Europa's mantle, the minerals are chemically altered, producing a group of minerals called serpentine, along with molecular hydrogen and heat. The reaction is exothermic. It releases energy, and the hydrogen it produces is a powerful fuel for certain types of microorganisms. On Earth, serpentinization occurs wherever water meets fresh ultramafic rock, at mid-ocean ridges, in ophiolites, in deep fractures in the continental crust, and it supports thriving microbial communities in some of the most extreme environments on our planet. In the Lost City hydrothermal field in the mid-Atlantic, tall chimneys of carbonate rock, some over 60 meters high, have been built by the slow precipitation of minerals from serpentinization-driven fluids. And the communities of microbes that live within and around these chimneys derive their energy entirely from the hydrogen and methane produced by water-rock reactions, with no connection to sunlight or to the kind of high-temperature volcanic venting found at black smokers. If serpentinization occurs on Europa's seafloor, and there is no reason it should not, given that the rocky mantle is expected to contain the right minerals, and the ocean provides abundant water, then hydrogen is being produced continuously, diffusing into the ocean, available as an energy source for organisms called methanogens. Methanogens are among the oldest lineages of life on Earth, archaea that combine hydrogen with dissolved carbon dioxide to produce methane and energy, thriving in environments without oxygen, without sunlight, without any of the conditions that we typically associate with life. A methanogen on Europa's seafloor would not need hydrothermal vents, it would not need volcanic heat, it would need only hydrogen from serpentinization, carbon dioxide dissolved in the ocean, and liquid water to live in. All three are plausibly available on Europa. The chemical evolution of Europa's ocean, driven by the slow dissolution of the seafloor combined with the delivery of oxidants from above, may have produced a chemistry that is uniquely suited to life, even without the dramatic pyrotechnics of hydrothermal vents. The ocean may have a gradient, oxidants delivered from above, reductants produced from below, and it is exactly this kind of chemical gradient that life on Earth exploits. Every living cell is, at its most fundamental level, a device for harvesting energy from chemical gradients. Europa's ocean may provide the gradient. Whether anything has evolved to exploit it is the question that Europa Clipper is designed to help answer. The bottom line is this: the question of whether Europa's ocean is habitable is not settled by a single study. It is being refined, year by year, paper by paper, as models become more sophisticated and observations provide more constraints. The pessimistic scenario, a quiet seafloor and no energy for life, has been challenged by the optimistic scenario, a top-down delivery of nutrients powered by radiation. The truth is probably somewhere in between, and it is exactly this kind of nuanced, evolving understanding that Europa Clipper is designed to advance. This is shocking discovery number 3. The Juno flyby revealed the ice shell, and it is thicker than we hoped. On September Taninitic, NASA's Juno spacecraft, which had been orbiting Jupiter since 2016, primarily studying the giant planet itself, made its closest ever flyby of Europa, passing just 352 kilometers above the surface. It was the closest any spacecraft had come to Europa since Galileo's final flyby in January 2000, more than 22 years earlier. Juno's cameras captured stunning images of Europa's surface in unprecedented detail. Images that revealed individual ice blocks, fresh ridges, and features as small as 1 kilometer across. But the most important data came not from the cameras, but from Juno's microwave radiometer, an instrument designed to peer beneath the surface by measuring microwave radiation emitted from within the ice shell. The results, published in 2025 in the journal Nature Astronomy, provided the first direct measurement of Europa's ice shell structure. The microwave radiometer detected a temperature profile consistent with solid ice extending to a depth of approximately 29 kilometers, nearly 30 kilometers of frozen, solid ice above the liquid ocean. This was thicker than some optimistic estimates had suggested, though within the range of theoretical predictions. 29 kilometers. To put that in perspective, the deepest hole ever drilled on Earth, the Kola Super Deep borehole in Russia, reached a depth of about 12.3 kilometers, and it took 20 years to drill. Europa's ice shell is more than twice that thick. Drilling through it with current technology would be extraordinarily difficult, perhaps impossible, with any mission that could be launched in the foreseeable future. But Juno also found something intriguing within the ice. The microwave data suggested that the ice shell is not uniform. It has a complex internal structure with layers that may include regions of warmer ice, pockets of brine, or other anomalies that break up the monotony of the solid ice. The shell is not a simple, featureless barrier. It is a dynamic, layered structure, a geological environment in its own right, potentially hosting its own chemistry, its own fluid dynamics, and its own processes for transporting material between the surface and the ocean. The thickness of the ice shell has direct implications for Europa Clipper's mission. The spacecraft carries an ice-penetrating radar instrument called REASON. Radar for Europa assessment and sounding, ocean to near surface, that is designed to peer through the ice and characterize its internal structure. REASON operates at 2 frequencies, allowing it to probe different depths within the ice. Whether it can detect the ocean itself, the interface between ice and liquid water at a depth of 30 kilometers, depends on the properties of the ice. If the ice is cold, pure, and relatively transparent to radar, REASON may be able to see all the way to the ocean. If the ice is warm, salty, or contains significant amounts of briny inclusions, the radar signal may be absorbed or scattered before reaching the bottom. Either way, REASON will reveal the internal architecture of the ice shell in unprecedented detail, mapping the layers, the brine pockets, the warm ice, and the cold ice, and building a 3-dimensional picture of the barrier that separates us from Europa's ocean. This is shocking discovery number 4. Europa's surface is painted with the chemistry of its ocean. When you look at Europa through a telescope or in spacecraft images, the most striking features, after the smoothness and the linea, are the colors. Most of Europa's surface is pale white or pale blue-gray, the natural color of clean water ice, but along the linea, in the chaos regions, and scattered across the surface in irregular patches, the ice is stained reddish-brown. These discolorations have fascinated scientists since the Voyager flybys in 1979, and their origin has been debated for decades. The reddish-brown material is not ordinary dirt or rock dust. Spectroscopic analysis, breaking the reflected light into its component wavelengths and analyzing the absorption features, has identified several components. There are hydrated salts, minerals that have incorporated water into their crystal structure. there is sulfuric acid hydrate, a compound formed when sulfur from Io's volcanoes is implanted into Europa's surface by Jupiter's magnetosphere and reacts with the water ice. And there may be organic compounds, complex carbon-based molecules that could originate from the ocean below. In 2009, astronomers using the Hubble Space Telescope identified sodium chloride, ordinary table salt, on Europa's surface, concentrated on the trailing hemisphere. This was significant because sodium chloride is the dominant salt in Earth's oceans, and its presence on Europa suggests that the composition of Europa's ocean may be more similar to Earth's than previously thought. Earlier analyses had suggested that Europa's ocean was dominated by magnesium sulfate, Epsom salt, which would be less favorable for life as we know it. The detection of sodium chloride shifted the picture toward a more Earth-like ocean chemistry. The colored material along the lineae is particularly telling. If the lineae form when the ice shell cracks and ocean material wells up from below, then the material deposited along the lineae is literally a sample of the ocean water that has reached the surface, frozen, and been modified by radiation. The reddish-brown color may be the result of radiation processing of organic compounds or salts from the ocean. In other words, Europa is displaying the chemistry of its hidden ocean on its surface, like a patient whose blood work is visible on their skin. There is something else about Europa's surface that deserves attention, because it connects to the question of habitability in a way that was not fully appreciated until recently. The radiation that bombards Europa's surface does not just create accidents, it also creates a thin atmosphere. Well, not exactly an atmosphere in the way we think of one. No wind, no weather, no breathable air. It is an exosphere, an extraordinarily tenuous envelope of gas, so thin that the individual molecules rarely collide with each other. The dominant component is molecular oxygen, produced when radiation breaks apart water ice molecules on the surface, and the freed hydrogen, being light, escapes to space, while the heavier oxygen lingers near the surface. This oxygen exosphere was first detected definitively by the Hubble Space Telescope in 1995, which observed ultraviolet emission lines consistent with atomic oxygen around Europa. The amount of oxygen is tiny by earthly standards. The surface pressure on Europa is roughly a trillionth of Earth's atmospheric pressure, essentially a vacuum. But its presence is significant. Oxygen is one of the most reactive and energy-rich molecules in chemistry. On Earth, oxygen is the fuel that powers nearly all complex life. If even a fraction of Europa's surface oxygen makes it through the ice shell and into the ocean, carried by the brine pockets and chaos terrain cycling we discussed earlier, it could provide a substantial source of chemical energy for any organisms living there. How much energy? A 2009 study estimated that the rate of oxygen delivery to Europa's ocean, if the ice shell cycles efficiently, could support a biomass equivalent to about the fish population of Earth's oceans. That is a stunning number. Not microscopic traces of life, but a potentially robust biosphere powered entirely by radiation-produced oxygen delivered through ice. The estimate involves many uncertainties, and the actual biomass could be far less or zero, but it shows that the energy budget, at least in principle, is more than sufficient for life. This is why Europa Clipper does not need to land. The ocean's chemistry is written on the surface, waiting to be read. This is shocking discovery number 5. Jupiter's Galilean system is a family of extremes, and Europa is not the only ocean world. To understand Europa fully, we need to understand the system it lives in, because Jupiter's 4 large moons are not isolated worlds. They are a family, bound by gravity, shaped by their relationships with each other and with their enormous parent planet. And each one is extraordinary in its own way. Let us start with Io, the innermost Galilean moon, orbiting just 422,000 kilometers from Jupiter. Io is the most volcanically active body in the solar system, more volcanically active than Earth, more volcanically active than any world we have ever observed. Its surface is covered with more than 400 active volcanoes, calderas up to 200 kilometers across, lava lakes of molten silicate rock glowing orange and yellow, and erupting plumes that shoot sulfur dioxide gas hundreds of kilometers above the surface. When Voyager 1 flew past Io in March 1979, navigation engineer Linda Morabito spotted an enormous umbrella-shaped plume rising 300 kilometers above the moon's limb, the first volcanic eruption ever witnessed on another world. Within days, 9 active eruptions had been identified. Io was not just volcanically active, it was erupting everywhere, simultaneously, in a frenzy of geological energy that dwarfed anything on Earth. The colors are surreal: yellows, oranges, reds, blacks, and whites, painted by sulfur and sulfur dioxide in various allotropic forms. Io looks like a pizza, as one scientist famously described it after the Voyager flyby. Io's volcanism is driven by the same mechanism that heats Europa, tidal heating. But Io is much closer to Jupiter, and the tidal forces are correspondingly much stronger. The tidal heating in Io is so intense that the moon's entire interior is partially molten, a global magma ocean lurking beneath the thin, constantly overturned crust. Io loses heat so fast that its surface is one of the youngest in the solar system. No impact craters survive for long before being buried by fresh lava. Io is relevant to Europa for 2 reasons. First, the Laplace resonance that maintains Europa's orbital eccentricity, and therefore its tidal heating, is anchored by Io. Without Io, the resonance would not exist. Europa's orbit would circularize, the tidal heating would stop, and the ocean would freeze solid. Europa owes its ocean to Io. The tidal heating on Io is astonishing in its magnitude. Io dissipates roughly 100 trillion watts of tidal energy, about 10 times the total energy consumption of human civilization. This energy is what drives the constant volcanic resurfacing. The lava erupted on Io reaches temperatures of over 1700 degrees Celsius, hotter than any terrestrial lava, suggesting that Io's magma is composed of ultramafic silicates, a type of rock so hot and so fluid that it has not erupted on Earth's surface for billions of years. Io is erupting rocks from an earlier age of the solar system, rocks that Earth's interior has long since cooled past. Juno, during its close flybys of Io in late 2023 and early 2024, revealed that the moon's volcanic activity is concentrated along the equator and that the interior has a global magma ocean layer about 50 kilometers beneath the surface. This magma ocean is not a solid mantle with pockets of melt. It is a continuous layer of liquid rock, maintained by the relentless tidal flexing. Io is, in some sense, turned inside out by Jupiter's gravity, its molten interior continuously erupting onto the surface, resurfacing the entire moon every few thousand years. Second, Io is the primary source of the plasma that fills Jupiter's magnetosphere. The volcanic gases ejected from Io, primarily sulfur dioxide, are ionized by Jupiter's radiation, creating a donut-shaped ring of plasma called the Io plasma torus that encircles Jupiter. This plasma is swept up by Jupiter's rapidly rotating magnetic field and accelerated outward, where it bombards the surfaces of Europa, Ganymede, and Callisto. The radiation that processes Europa's surface ice and creates the oxidants that may feed the ocean, that radiation originates, ultimately, from Io's volcanoes. In a sense, Io's volcanism feeds Europa's ocean through a chain of physical processes that spans hundreds of thousands of kilometers. Tidal heating produces volcanism on Io. Volcanism supplies plasma to Jupiter's magnetosphere. The magnetosphere accelerates the plasma into Europa's surface. The radiation produces oxidants in the ice, and the ice shell delivers the oxidants to the ocean. It is a Rube Goldberg machine of astrobiology, powered by gravity and connected by magnetic fields. Now let us move outward to Ganymede, the third Galilean moon and the largest moon in the entire solar system. Ganymede is about 5,268 kilometers in diameter, larger than the planet Mercury, though less massive because it is made partly of ice rather than entirely of rock and metal. If Ganymede orbited the Sun instead of Jupiter, it would be classified as a planet. Ganymede is the only moon in the solar system known to generate its own magnetic field, a dipolar field, like a bar magnet produced by convection currents in a liquid iron core deep inside the moon. This magnetic field creates a miniature magnetosphere around Ganymede, a bubble within Jupiter's much larger magnetosphere that produces its own auroral emissions, observed by the Hubble Space Telescope as glowing bands of ultraviolet light near the moon's poles. Ganymede's surface tells a story of two epochs. About half of the moon is covered in dark, ancient, heavily cratered terrain, old ground that dates back billions of years, recording the early bombardment history of the solar system. The other half is covered in lighter, grooved terrain, younger ground marked by long, parallel sets of ridges and troughs that suggest the surface was deformed by tectonic processes at some point in the past. The grooved terrain is evidence that Ganymede was once geologically active, that internal forces stretched and cracked and reshaped the surface, though the activity appears to have ceased long ago. Ganymede today is quiet, its geological youth behind it, its surface slowly accumulating new craters in the patient bombardment of deep time. Beneath this dual surface lies ice, hundreds of kilometers of ice, and somewhere within or below that ice, liquid water. And it was the auroral observations from Hubble that provided the key evidence for Ganymede's ocean. In 2015, a team led by Joachim Sauer at the University of Cologne used Hubble to observe Ganymede's aurorae over multiple orbits. If Ganymede had no ocean, if it were solid ice and rock all the way through, then its aurorae would wobble back and forth by about 6 degrees as Jupiter's magnetic field rotated. But if a conducting layer of saltwater existed beneath the ice, the ocean would partially counteract Jupiter's magnetic influence, reducing the auroral wobble. Sauer's observations showed that the aurorae wobbled by only about 2 degrees, far less than expected for a dry interior and consistent with a global saltwater ocean about 100 kilometers beneath the surface. Ganymede's ocean is thought to be sandwiched between layers of ice. A high-pressure ice layer below the ocean, resting on the rocky mantle, and the familiar ice one layer above the ocean, forming the visible surface. This layered structure is very different from Europa's, where the ocean sits directly on top of the rocky seafloor. On Europa, ocean water can interact directly with rock, a condition that is favorable for the kinds of chemical reactions that support life on Earth, the serpentinization and water-rock chemistry we discussed earlier. On Ganymede, the ocean may be isolated from the rock by a layer of high-pressure ice, potentially limiting the chemical exchange between water and rock. The high-pressure ice is not ordinary ice. Under the immense pressures deep inside Ganymede, pressures hundreds of times greater than the pressure at the bottom of Earth's deepest ocean trenches, water ice takes on exotic crystal structures that do not exist on Earth's surface. These are called ice phases: Ice 3, Ice 5, Ice 6, each with a different arrangement of water molecules, each stable at a different combination of pressure and temperature. These high-pressure ice phases are denser than liquid water, so they sink to the bottom of the ocean and form a solid layer between the liquid water above and the rocky mantle below. Some models suggest that Ganymede's interior may contain multiple layers of ocean separated by different ice phases, a kind of geological layer cake of water, ice, with the rocky core at the center. Whether salts, nutrients, or chemical energy can diffuse through these ice layers is an open question, one that JUICE is specifically designed to address. This does not mean Ganymede's ocean is uninhabitable, but it means the conditions are less obviously favorable than Europa's. Ganymede is the primary target of ESA's JUICE mission, Jupiter Icy Moons Explorer, which launched on April 14, 2023, and is expected to arrive at Jupiter in July 2021. JUICE will make multiple flybys of Europa and Callisto before entering orbit around Ganymede in December 2024, the first time any spacecraft has orbited a moon other than Earth's moon. Its instruments will characterize the ice shell, the ocean, and the magnetic field in unprecedented detail, answering questions that Hubble's observations could only raise. And finally, Callisto, the outermost Galilean moon, orbiting nearly 2 million kilometers from Jupiter. Callisto is the third largest moon in the solar system, about 4,821 kilometers in diameter, almost as large as Mercury. And it is, in many ways, the opposite of its siblings. Callisto's surface is ancient, staggeringly ancient. It is the most heavily cratered object in the solar system, a surface so saturated with impact craters that new impacts simply overlap old ones, creating a palimpsest of destruction that records billions of years of bombardment. There are no signs of geological activity, no lineae, no chaos terrain, no volcanic features, no evidence of surface renewal of any kind. Callisto appears to be geologically dead, a world frozen in time since the earliest ages of the solar system. And yet, the Galileo spacecraft detected hints of a subsurface ocean on Callisto as well. Like Europa, Callisto showed evidence of an induced magnetic field, a field that responded to Jupiter's rotating magnetosphere in a way consistent with a conducting layer beneath the surface. The signal was weaker than Europa's, and the interpretation is less certain, but the data suggest that even Callisto, the most inert, most ancient, most geologically dead world in the Jovian system, may harbor liquid water somewhere deep beneath its battered surface. If Callisto has an ocean, it is a profound mystery. Callisto has no orbital resonance with the other moons, no mechanism for tidal heating. Its interior should be cold. How does it maintain liquid water? One possibility is antifreeze. Dissolved ammonia or salts in the water could lower the freezing point enough to keep a thin layer liquid at relatively low temperatures. Another is that residual heat from Callisto's formation, combined with radioactive decay of elements like potassium, uranium, and thorium in its rocky component, and the insulating properties of the thick ice shell has been enough to prevent the ocean from freezing completely over 4.5 billion years. Callisto is also puzzling for another reason. Unlike the other Galilean moons, Callisto appears to be only partially differentiated, meaning that its interior has not fully separated into distinct layers of rock and ice. Europa and Ganymede have clearly differentiated interiors, dense rock and metal at the center, lighter ice and water above. But Callisto seems to be a more uniform mixture of rock and ice throughout, as if it never fully melted and separated during its formation. This is strange because Ganymede, which is nearly the same size and composition as Callisto, did differentiate. Why did one moon melt and the other did not? One hypothesis involves the tidal heating history. Ganymede, locked in the Laplace resonance with Europa and Io, may have experienced periods of intense tidal heating early in its history that melted its interior and drove differentiation. Callisto, orbiting beyond the resonance, escaped this heating and remained partially mixed. If this is correct, then the Laplace resonance has shaped not just the surfaces of the Galilean moons, but their very internal structures, determining which ones melted, which ones differentiated, and which ones developed the conditions for liquid water oceans. Callisto has one more claim to fame that connects it to the human future. Because it orbits far enough from Jupiter to be outside the most intense regions of the radiation belts, Callisto has been proposed as a potential base for human exploration of the Jupiter system. A crewed outpost on Callisto's surface would be shielded from the worst of Jupiter's radiation by distance alone, and could serve as a staging point for remotely operated missions to Europa and the other moons. It is a long-term vision, decades or centuries away, but it shows how the Galilean moons are interconnected in our thinking about the future as well as the past. Their Galilean system, then, presents us with a spectrum of ocean worlds, from Io, which is too hot and too volcanic for liquid water, to Europa, which has a rocky seafloor and intense tidal heating, to Ganymede, which has a deep ocean sandwiched between ice layers, to Callisto, which may have an ocean despite having no obvious heat source. 4 moons, 4 different relationships between ice and water, and rock and heat. 4 different experiments in habitability, running simultaneously, orbiting the same planet. This is shocking discovery number 6. Europa Clipper, the most ambitious ocean world mission ever built. Right now, as you listen to these words, a spacecraft is crossing the solar system on its way to Jupiter. It is the largest interplanetary spacecraft NASA has ever built for a planetary mission, a colossus of engineering, bristling with instruments, armored against radiation, and carrying with it the hopes of an entire generation of planetary scientists. Europa Clipper launched on October 14th, 2024, from Kennedy Space Center in Florida, aboard a SpaceX Falcon Heavy rocket. The launch itself was a triumph, the culmination of more than 2 decades of planning, advocacy, and engineering. The concept of a dedicated Europa mission had been studied since the late 1990s, when the Galileo data first made the case for an ocean. Multiple mission concepts were proposed, studied, cancelled, revised, and reproposed over the years. The original vision, a Europa orbiter, was eventually judged too risky, because an orbiter would spend too much time in Jupiter's radiation belts and would accumulate a lethal dose of radiation too quickly. The solution was the Clipper concept, a spacecraft that orbits Jupiter, not Europa, swooping close to the Moon during each pass and then retreating to safer distances. This approach minimizes the total radiation exposure while still allowing close-up science during each flyby. The mission nearly did not happen. In the early 2010s, NASA considered canceling the Europa mission due to budget constraints. It was saved by a combination of scientific advocacy and congressional support, particularly from Congressman John Culberson of Texas, who championed Europa funding for years, driven by a personal fascination with the possibility of life beyond Earth. The mission was formally approved in 2015, and construction began at NASA's Jet Propulsion Laboratory in Pasadena, California. Europa Clipper is scheduled to arrive at Jupiter in April 2030 after a journey of nearly 6 years that includes gravity assists from Mars, which it flew past on March 1, 2025, using the red planet's gravity to bend its trajectory, and from Earth in December 2026 to build up the speed needed to reach the outer solar system. During the Mars flyby, several of Europa Clipper's instruments were activated and calibrated, using Mars as a test target. The first science data from a spacecraft designed to study a moon of Jupiter, collected at a planet that is itself a target of intense astrobiological interest. The spacecraft is enormous. With its solar panels fully deployed, Europa Clipper spans about 30 meters from tip to tip, roughly the width of a basketball court. This is driven by necessity. At Jupiter's distance from the Sun, about 5 times the distance from Earth to the Sun, sunlight is only about 4% as intense as at Earth. The enormous solar panels are needed to generate enough electricity to power the spacecraft's instruments and systems. Europa Clipper is the first NASA mission to the outer solar system to use solar panels rather than nuclear power. A decision driven by the availability and cost of plutonium-238, the fuel used in radioisotope thermoelectric generators. The spacecraft carries 9 scientific instruments, each designed to study a different aspect of Europa. There is REASON, the ice-penetrating radar that will peer beneath the surface. There is the Europa imaging system, a pair of cameras, wide-angle and narrow-angle, that will photograph the surface at resolutions as fine as half a meter per pixel, revealing features smaller than a parked car. There is the Europa thermal emission imaging system, which will map the surface temperature, searching for warm spots that might indicate recent geological activity or thin ice over subsurface water. There is the Mapping Imaging Spectrometer for Europa, which will map the composition of the surface, identifying salts, organics, and other compounds. There is the Surface Dust Analyzer, SUDA, which will capture and analyze individual particles of ice and dust ejected from Europa's surface by micrometeorite impacts, essentially tasting the surface material as the spacecraft flies past. There is the Mass Spectrometer for Planetary Exploration, MASSPEX, which will sample any gases or volatiles in Europa's extremely thin atmosphere or in any plumes that might be active during the flybys. And there are magnetometers, a plasma instrument, and a gravity science investigation that will characterize the ocean's depth, salinity, and global extent. But Europa Clipper will not orbit Europa. It cannot. Jupiter's radiation belts are so intense near Europa's orbit that the spacecraft's electronics would be destroyed within weeks if it remained in close proximity. Instead, Europa Clipper will orbit Jupiter on a highly elliptical path, swinging close to Europa during each orbit, conducting a targeted flyby, collecting data at close range, and then retreating to a safer distance to transmit the data back to Earth before the radiation can cause permanent damage. Over the course of its primary mission, Europa Clipper will make 49 close flybys of Europa, approaching as close as 25 kilometers above the surface, closer than any spacecraft has ever flown over this moon. Each flyby will cover a different region of the surface, and over the course of 49 passes, the spacecraft will build up a near-complete map of Europa in visible light, infrared, radar, and thermal emission. It will not see everything. Some regions will be in shadow during the flyby, some will be obscured by the viewing geometry. But by the time the primary mission is complete, we will have a more detailed understanding of Europa's surface, ice shell, and ocean than we have of many regions on Earth. The radiation environment is the mission's greatest challenge. Jupiter's magnetosphere traps enormous quantities of high-energy particles, electrons, protons, and heavy ions that bombard everything near the planet. At Europa's orbit, the radiation dose is intense enough to damage or destroy unshielded electronics within days. Europa Clipper's sensitive electronics are housed in a radiation vault, a box with walls made of aluminum and zinc, about a centimeter thick, that shields the computers and processors from the worst of the radiation. The vault reduces the radiation exposure by a factor of about 800, extending the operational lifetime of the electronics from days to years. Even with the vault, the accumulated radiation dose over the course of the mission will be enormous. The transistors and circuits inside the vault are specially hardened, designed to tolerate radiation levels far beyond what any consumer electronics could survive. Every component has been tested, irradiated, and retested. The mission engineers have calculated the total accumulated dose over the primary mission and designed every system to survive it, with margin. The spacecraft also carries a message. Engraved on a metal plate attached to Europa Clipper's body is a poem by the American poet Ada Limon, titled In Praise of Mystery, a poem for Europa. The poem was selected through a collaboration between NASA and the US Poet Laureate, and it reflects on the human longing to connect with other forms of life. The plate also includes a microchip containing the names of over 2.6 million people from around the world who signed up to have their names sent to Jupiter, a digital passenger manifest for a voyage that most of them will never see completed. And on the other side of the plate is a representation of the Drake equation, the famous formula that attempts to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. It is a fitting emblem for a mission that seeks to address one of the equation's key variables: how often does life arise given the right conditions? Europa Clipper also carries a scientific tribute to the water molecule, an engraving of the word water in 103 languages, arranged in a waveform pattern that evokes the electromagnetic signature of water as detected by radio telescopes. It is a celebration of the substance that connects Earth to Europa, that makes both worlds wet, and that may, in its liquid form, serve as the medium for life in two separate locations in the same solar system. There is something deeply human about this. We are sending a machine into one of the most hostile radiation environments in the solar system, armored and hardened and shielded, carrying a poem and 2 million names and the word for water in 100 languages, to study a world that may harbor life in its dark ocean. The radiation that may be feeding Europa's ocean is the same radiation that threatens to destroy the spacecraft studying it. Europa Clipper must survive the very thing that may make Europa habitable. The radiation at Europa's orbit is staggering. A human standing unprotected on Europa's surface would receive a lethal dose of radiation in less than a day, roughly 500 rem, enough to cause acute radiation syndrome, and death within weeks. Their radiation comes primarily from electrons and ions trapped in Jupiter's magnetic field, the most powerful planetary magnetic field in the solar system, about 20,000 times stronger than Earth's. These particles are accelerated to enormous energies as they spiral along magnetic field lines, and they slam into Europa's surface and anything orbiting nearby with the force of tiny, invisible bullets. The total radiation dose at Europa's orbital distance is roughly 540 rem per day, a value that makes the International Space Station at about 150 millirem per day look like a shielded bunker. This is why Europa Clipper uses the flyby strategy rather than orbiting Europa directly. Each flyby exposes the spacecraft to intense radiation for only a few hours, after which it retreats to a more distant orbit where the particle density is much lower. The total accumulated dose over the entire mission, 49 flybys spread over several years, is carefully budgeted. Every component, every wire, every circuit board has been designed to withstand a specific total dose, and the mission plan ensures that the dose is never exceeded. It is a delicate dance between science and survival, between the desire to get close and the need to stay alive. The radiation also affects the science in unexpected ways. When high-energy particles strike the spacecraft's detectors, they produce spurious signals, false readings that can mimic the signatures of real physical processes. The science team has developed sophisticated algorithms to distinguish true signals from radiation noise, but the challenge increases with each flyby as the accumulated radiation degrades the sensitivity of the instruments. The last flybys will be the most scientifically challenging, conducted with instruments that have been subtly damaged by years of radiation exposure, reading signals through a growing haze of electronic noise. And yet those final flybys may also be the most scientifically valuable, because they will target regions that were not covered earlier in the mission, filling in the last gaps in the global map. This is shocking discovery number 7. The solar system is full of hidden oceans, and Europa may be just the beginning. When scientists first proposed that Europa might have a subsurface ocean, it was a radical idea. Water in liquid form, sustained not by sunlight but by tidal heating, hidden beneath kilometers of ice on a frozen moon in the outer solar system. It seemed exotic, unlikely, a special case. It was not a special case. It was the rule. As our exploration of the solar system has progressed, the list of worlds suspected or confirmed to harbor subsurface oceans has grown steadily, until it has become clear that oceans are not rare in the outer solar system. They are common, perhaps ubiquitous. We have discussed Europa, Ganymede, and Callisto. We have talked about Enceladus in a previous episode, the tiny moon of Saturn that shoots its ocean into space through ice geysers at its south pole. We have talked about Titan with its surface methane seas and a possible water ocean deep beneath its icy crust. But the list goes on, extending far beyond the Jupiter system. Triton, Neptune's largest moon, a captured Kuiper Belt object orbiting the ice giant in a retrograde direction, shows signs of recent geological activity, including geysers of nitrogen gas observed by Voyager 2 during its flyby in August 1989, the only spacecraft encounter with Neptune's system to date. The geysers erupt from Triton's south polar region, shooting plumes of dark material 8 kilometers above the surface and trailing in the thin atmosphere for hundreds of kilometers downwind. Triton's surface is extraordinarily young, so sparsely cratered that some form of geological renewal must be occurring. The surface features include cantilap terrain, a bizarre, dimpled landscape that looks like the skin of a melon, and smooth, frozen plains of nitrogen ice. Triton's surface temperature is only about minus 235 degrees Celsius, making it one of the coldest surfaces in the solar system. And yet, it shows signs of activity that suggest heat beneath the ice. Models suggest that tidal heating from Triton's eccentric, retrograde orbit could maintain a subsurface ocean of liquid water, possibly mixed with ammonia as an antifreeze. Pluto, the former planet, now dwarf planet, orbiting in the cold outer reaches of the Kuiper Belt, nearly 6 billion kilometers from the Sun, showed evidence during the New Horizons flyby in July 2015 of a possible subsurface ocean beneath the Sputnik Planitia Basin. Sputnik Planitia is the western lobe of the heart-shaped feature that captured the world's imagination when the first close-up images were released. A vast plain of nitrogen ice, roughly 1,000 kilometers across, smooth and crater-free, slowly churning in convection cells like a pot of very thick, very cold soup. The basin sits near the equator and is roughly aligned with the Pluto-Charon tidal axis, a location that is consistent with an extra mass concentration beneath the surface. If the basin were simply a hole, a depression without extra mass, it would have migrated away from the tidal axis over time. The fact that it sits right on the axis suggests that something heavy lies beneath it, pulling it into alignment. The most plausible candidate is a layer of liquid water, perhaps mixed with ammonia to lower its freezing point, that has not yet frozen completely despite surface temperatures of minus 230 degrees Celsius. Subsequent studies have strengthened the case. Analysis of the fracture patterns on Pluto's surface, long extensional faults radiating outward from Sputnik Planitia, is consistent with the gradual freezing and expansion of an internal ocean, which would stretch and crack the icy crust above it. The pattern looks remarkably similar to the fractures seen on Europa, scaled to a different world. If Pluto, tiny, distant, frigid Pluto, orbiting in the outermost reaches of the solar system, billions of kilometers from the nearest significant heat source, has liquid water beneath its surface, then the conditions for subsurface oceans are even less restrictive than we imagined. Even Ceres, the largest object in the asteroid belt, a dwarf planet only 940 kilometers in diameter, showed evidence from NASA's Dawn mission of briny liquid water beneath its surface, erupting through cracks and depositing bright salt deposits in craters like Okator. When Dawn arrived at Ceres in 2015, the bright spots in Okator crater, the brightest features on an otherwise dark, unremarkable surface, created a sensation. What were they? Ice? Salt? Something else? Dawn's instruments eventually revealed that they are deposits of sodium carbonate, a salt left behind when briny water from beneath the surface erupted and evaporated in the vacuum of space. The eruptions were recent, perhaps within the last few million years, possibly even more recently. Ceres is not an ice moon orbiting a gas giant. It is a small, rocky, icy body in the inner solar system, with no giant planet to provide tidal heating. And yet it too harbors liquid water beneath its surface, maintained perhaps by the residual heat of radioactive decay in its rocky interior. The pattern is unmistakable. Everywhere we look in the solar system, from the innermost giant planet to the outermost reaches of the Kuiper Belt, we find worlds with liquid water beneath their surfaces. The conditions that produce subsurface oceans are not rare or special. They are common. They require only a body large enough to retain some internal heat, a crust of ice thick enough to insulate, and enough time for the interior to warm. The solar system is not a collection of dry, dead rocks orbiting a star. It is a collection of hidden oceans, buried beneath ice, distributed across a vast range of distances and conditions, each one a potential habitat for life. The emerging picture is remarkable, and it extends even further than our own solar system. In recent years, astronomers studying exoplanets, planets orbiting other stars, have begun to realize that ice-covered ocean worlds may be among the most common types of habitable worlds in the universe. Many of the exoplanets detected by the Kepler and TESS space telescopes orbit too far from their stars for liquid surface water, but they could easily have subsurface oceans beneath thick ice shells, warmed by internal heat from radioactive decay or from tidal interactions with other planets or moons. Some models suggest that for every Earth-like planet with liquid water on its surface, there may be dozens or hundreds of ice-covered ocean worlds scattered through the galaxy. If this is correct, then the vast majority of habitable environments in the universe look not like Earth, but like Europa, dark, cold, ice-covered, and hidden. Liquid water, the essential solvent for life as we know it, is not confined to the surfaces of planets in the habitable zone, the narrow band around a star where temperatures allow liquid water to exist on a planet's surface. Liquid water exists throughout the solar system, hidden beneath ice, maintained by tidal heating, radioactive decay, antifreeze chemistry, and insulation. The habitable zone, as traditionally defined, may be almost irrelevant for ocean worlds. A moon orbiting a gas giant at any distance from its star could have liquid water as long as the tidal heating is sufficient and the ice shell is thick enough to insulate. This has profound implications for the search for life in the universe. When we search for habitable worlds around other stars, when we point our telescopes at distant solar systems and look for planets in the habitable zone, we are looking for worlds like Earth, with liquid water on their surfaces, warmed by starlight. But what if most of the habitable real estate in the universe is not on planetary surfaces at all? What if most of the liquid water and most of the potential habitats for life are hidden beneath ice, on moons of gas giants, in the cold outer reaches of planetary systems where we cannot see them? The universe may be full of Europas, full of Enceladuses, full of ocean worlds, hiding their water beneath shells of ice, powered by tidal heating, harboring conditions that could support life, and we would never know it from the outside. These worlds do not announce themselves. They do not reflect starlight in the telltale way that liquid surface water would. They are invisible to our telescopes, hidden in the dark, keeping their secrets beneath the ice. If life exists on Europa, even the simplest microbial life, even the chemical residue of life that once existed, it would transform our understanding of the universe. It would mean that life does not require sunlight. It does not require a planetary surface. It does not require the narrow, specific conditions of Earth's habitable zone. It requires only liquid water, chemistry, and energy. And these are available, it seems, throughout the universe in the most unexpected places. Arthur C. Clarke, the science fiction writer who imagined alien life beneath Europa's ice in his novel 2010, Odyssey 2, ended his fictional warning with the famous message, "All these worlds are yours except Europa. Attempt no landing there." In Clarke's story, the warning was meant to protect the life developing in Europa's ocean from contamination by human visitors. We are not landing on Europa. Not yet. But we are going. Europa Clipper is crossing the solar system right now, millions of kilometers closer to Jupiter with every passing day. JUICE is on its way as well, carrying 11 scientific instruments designed to complement the American mission's focus on Europa, with a broader study of the entire Jovian system. JUICE will make 2 flybys of Europa, multiple flybys of Callisto, using Callisto's gravity to gradually reshape its orbit, and ultimately enter orbit around Ganymede in late 2034, becoming the first spacecraft ever to orbit a moon of another planet. Where Europa Clipper focuses on Europa's habitability, JUICE focuses on Ganymede's ocean, magnetic field, and geological history, while also characterizing the Jupiter system as a whole, its magnetosphere, its atmosphere, and the interactions between the planet and its moons. Together, Europa Clipper and JUICE represent the most ambitious campaign of outer solar system exploration ever undertaken. 2 spacecraft from 2 space agencies studying the same system from complementary perspectives. The data they return will be combined, compared, and cross-referenced, building a picture of the Jovian system that neither mission could achieve alone. And beyond these 2 missions, the planning has already begun for what comes next. Multiple mission concepts for a Europa lander have been studied. Small, targeted landers that would touch down on the ice surface, possibly in a chaos region or near a fresh fracture, and analyze the surface material with instruments far more sensitive than anything on an orbiting spacecraft. A lander could search directly for organic molecules, amino acids, lipid membranes, and other biosignatures in the ice. It could measure the isotopic ratios of carbon and sulfur, measurements that on Earth distinguish biological from non-biological chemistry with high confidence. It could even look for cellular structures, the physical forms of life, frozen in the ice, preserved by the cold. A lander mission is harder than a flyby mission. It requires navigating to a specific location on an icy surface with extreme precision, surviving the landing impact, operating in the intense radiation environment for long enough to conduct its measurements, and transmitting the data back through the ice and across the solar system. The engineering challenges are enormous, but they are not insurmountable. And the prize, the definitive detection or exclusion of life on another world, justifies the effort. In a few years, we will have 2 sophisticated spacecraft studying the Jovian system simultaneously, peering beneath the ice, tasting the surface chemistry, mapping the ocean, and searching for the signatures of life. The answer to the question, "Are we alone?" may not come from a radio signal from a distant star. It may not come from a fossil on Mars. It may come from a tiny, frozen moon orbiting a giant planet, where the chemistry of an ocean, hidden for billions of years beneath kilometers of ice, is finally revealed to the instruments of a spacecraft that we sent to look. Let us step back now and consider the larger picture. Not just the science of Europa, but the idea behind it. The idea that life might exist somewhere other than Earth. This is not a new idea. It is one of the oldest ideas in human thought. The ancient Greek philosopher Epicurus, writing in the 3rd century before the Common Era, argued that in an infinite universe there must be an infinite number of worlds, some of them inhabited. Giordano Bruno, in the 16th century, proposed that every star was a sun with its own planets, and that those planets might harbor life, an idea that contributed to his execution by the Inquisition in 1600. The idea of life beyond Earth has always been part speculation, part philosophy, part wish, but until the space age, it remained firmly in the realm of imagination, untested by observation. The 20th century changed that. The space age gave us the ability to visit other worlds, to study them close up, to test the soil and sniff the air and measure the chemistry. And the results were, at first, disappointing. The moon was barren, dry, airless, lifeless. Venus was a hellscape, crushed under 90 atmospheres of carbon dioxide, baked at over 450 degrees Celsius, with sulfuric acid clouds and no liquid water. Mars was the great hope, and the Viking landers of 1976 conducted the first direct search for life on another planet. The results were ambiguous at best, negative at worst. The biology experiments detected chemical reactions that mimicked some signatures of life, but the consensus interpretation was that the reactions were driven by inorganic chemistry in the oxidizing Martian soil, not by living organisms. Mars appeared to be sterile, dry, cold, irradiated, and lifeless. By the late 1970s, the search for life in the solar system seemed to be at a dead end. And then Voyager flew past Jupiter, and everything changed. Not because Voyager found life, it did not, but because it revealed that the conditions for life existed in places no one had considered. Europa's smooth, cracked surface suggested an ocean. Io's volcanoes demonstrated that tidal heating could generate enormous amounts of energy in the outer solar system. The Galilean moons were not the frozen, dead worlds that everyone had expected. They were dynamic, active, interesting, and potentially habitable. The discovery of hydrothermal vents on Earth's ocean floor in 1977, just 2 years before the Voyager-Jupiter encounters, provided the missing conceptual link. Here, on our own planet, entire ecosystems thrived in total darkness, at crushing pressures, nourished not by sunlight, but by chemical energy from hot, mineral-rich water erupting from the seafloor. If life could exist at the bottom of Earth's oceans in conditions completely independent of sunlight, then it could potentially exist in any dark, watery environment with a source of chemical energy, including the oceans of Europa. This convergence, Voyager's revelation of dynamic, watery moons, and the discovery of chemosynthetic life on Earth, is what launched the modern field of astrobiology. It is what made Europa the target it is today. The search for life shifted from the surfaces of planets where we could see to the interiors of moons where we could not. And the question changed from, is the surface habitable, to, is there liquid water, and if so, does it have the chemistry and energy to support life? We live in a solar system that is far more complex, far more dynamic, and far more hospitable than we imagined even a few decades ago. When the space age began, we expected to find a cosmos that was largely barren. A few rocky planets baking in sunlight, a few gas giants with their retinues of frozen, inert moons, and vast stretches of empty space in between. What we found instead was a solar system alive with hidden activity, hidden water, and hidden possibility. Europa sits at the center of this revolution. It is the world that taught us that oceans can exist without sunlight, that habitability does not require a star's warmth, that the ingredients for life can be assembled in darkness and cold and pressure, powered by gravity alone. Europa is not the only ocean world. It is not even the most accessible, since Enceladus conveniently shoots its ocean into space. But it is the archetype. It is the world that changed the question from where could life exist to where could life not exist. Consider what we have learned tonight. We have learned that Europa has a global saltwater ocean, 2 to 3 times the volume of all Earth's oceans, maintained by tidal heating from Jupiter's gravity. We have learned that the ocean is separated from space by an ice shell perhaps 30 kilometers thick, a barrier that is also a delivery system, transporting oxygen and nutrients from the radiation-blasted surface to the dark water below. We have learned that the surface chemistry reveals the composition of the ocean, written in salts and organics, and reddish-brown stains along the fractures in the ice. We have learned that Europa's seafloor may be quieter than we hoped, but that the ocean may feed from the top down, powered by Jupiter's radiation rather than by volcanic heat. We have learned that Europa is part of a family, the Galilean moons, each one a different experiment in the relationship between ice, water, rock, and heat. We have learned that Europa Clipper, the largest planetary spacecraft ever built, is on its way, carrying 9 instruments designed to read the story written on Europa's surface and within its ice. And we have learned the most remarkable thing of all: Europa is not unique. The solar system is full of ocean worlds: Enceladus, Ganymede, Callisto, Titan, possibly Triton, possibly Pluto, possibly Mimas, possibly Ceres, each one hiding liquid water beneath a shell of ice, each one a potential habitat for life, each one a reminder that the universe is stranger and richer and more generous than our expectations. The question is no longer whether liquid water exists beyond Earth. It does. The question is no longer whether the conditions for life exist beyond Earth. They do. The question now, the only question that remains, is whether life is there. Whether the chemistry of water and carbon and energy, given billions of years and the right conditions, produces life inevitably, as a natural, repeatable consequence of physics, or whether life is a singular miracle, an event so improbable that it happened once on Earth and never again. Europa Clipper cannot answer this question definitively. It is not designed to detect life directly. It does not carry a microscope or a culture medium or a DNA sequencer. What it can do is characterize the environment in enough detail to tell us whether the conditions are right, whether the ocean has the right chemistry, the right energy, the right materials. It can search for organic molecules on the surface and in the tenuous atmosphere. It can map the ice shell and look for places where ocean material has reached the surface recently. It can set the stage for the mission that comes after, the mission that will land on Europa, drill through the ice, lower an instrument into the dark water, and look. That mission does not exist yet. It has not been approved, or designed, or funded. But it will come. Because the question is too important not to answer, and Europa is too promising not to explore. The hardest part, crossing the solar system, surviving the radiation, reaching the ice, is being done now by Europa Clipper. Everything that follows will build on what it finds. There is a particular kind of courage in sending a machine across 1 billion kilometers of space to study a world we cannot visit ourselves. Europa Clipper will never return to Earth. It will spend years in the punishing radiation of Jupiter's magnetosphere, making its 49 flybys, collecting its data, transmitting its findings, and gradually succumbing to the radiation damage that will eventually silence its instruments and end its mission. It will join the growing family of spacecraft scattered across the solar system: Voyager, Galileo, Cassini, New Horizons, Pioneer, machines that carry our curiosity into places our bodies cannot go. But what it learns will come home. The data will cross the solar system at the speed of light, received by the deep space network's antennas on Earth, processed by scientists in laboratories and offices and universities around the world, published in papers and discussed at conferences and taught in classrooms and absorbed into the collective understanding of our species. What Europa Clipper finds will become part of what we know, part of the slowly growing body of knowledge that tells us what the universe is, where we came from, and whether we are alone. The ocean beneath Europa's ice has been there for billions of years. It has been dark, cold, silent, unknown. No eyes have ever seen it. No instrument has ever measured it. No light has ever penetrated the ice above it. It has simply existed, a vast, hidden body of salt water, flexed by Jupiter's gravity, possibly enriched by radiation-produced nutrients dripping through the ice, possibly harboring chemistry that we would recognize as life, possibly utterly sterile. We do not know which it is, not yet, but we are going to find out. Tonight, as you listen to these words, Europa is out there, a small, bright point of light in the sky orbiting Jupiter, reflecting sunlight off its icy surface, hiding its ocean beneath the ice. Europa Clipper is out there too, a spacecraft the size of a basketball court, crossing the dark between the planets, carrying instruments that may answer the oldest question our species has ever asked. The ice is thick, the ocean is deep, the distance is vast. But we built a machine, and we sent it, and it is on its way. And beneath the ice, in the dark, the ocean waits. It has been waiting for 4 billion years. It can wait a little longer. We are coming. So let tonight be gentle. Let the images settle. The cracked white ice of Europa catching the distant sunlight. The reddish-brown veins of ocean chemistry etched across its surface. The chaos terrain where warm ice has disrupted the frozen shell. The enormous bulk of Jupiter looming in the sky above. Imagine standing on Europa's surface. If you could survive the radiation, if you could endure the cold, looking up at a sky dominated by the largest planet in the solar system, a swirling sphere of clouds banded in amber and cream, its great red spot gazing down like an eye. The ground beneath your feet is ice, ancient ice, young ice, fractured ice, smooth ice, and beneath it, far below, hidden in darkness, an ocean larger than all the oceans of Earth, waiting. You do not need to remember the numbers. You do not need to remember the names of the instruments or the dates of the flybys. Just remember that out there, right now, orbiting a gas giant 5 times farther from the sun than Earth, there is a world with an ocean. A real ocean, with real water, with real salt, with real chemistry. An ocean that might, just might, harbor the second example of life in the universe. We sent a spacecraft to find out. It is on its way. And when it arrives and makes its first pass over that cracked, stained, impossibly smooth surface, and peers beneath the ice with its radar and its cameras and its spectrometers, when it sends its first data back across 1 billion kilometers of emptiness to the eager scientists waiting on Earth, we will begin to learn whether the ocean beneath Europa's ice is a cradle or a tomb. Either answer will change everything. The ice is thick, the ocean is deep, and somewhere between the two, between the frozen surface and the liquid dark, there may be a boundary where chemistry becomes biology, where molecules become cells, where matter becomes alive. Or there may not. The ocean may be sterile. The chemistry may be incomplete. The leap from molecules to life may be so improbable that it has happened only once, in all the universe, on a small rocky planet orbiting an ordinary star, in a quiet arm of an ordinary galaxy. We do not know, but we are asking. And asking, sending our machines into the dark, across impossible distances, to peer beneath the ice of alien worlds, is itself a kind of answer. It says something about what we are. We are a species that asks, that builds, that sends, that looks. The ocean does not know we are coming. Europa does not know it is beautiful. Jupiter does not know it has warmed the world. The ice does not know it is hiding something extraordinary. But we know, and so we go. The night is long, the stars are steady. Europa is out there, somewhere in the dark, orbiting its giant planet, turning slowly, catching the distant sunlight on its fractured ice. The lineae glow faintly reddish-brown, where the ocean's chemistry has stained the surface. The chaos terrain shifts imperceptibly, warm ice rising from below, cold ice sinking. The great slow cycle of material between ocean and sky continuing as it has for billions of years. And somewhere beneath all of it, beneath the radiation, beneath the ice, beneath the silence, the ocean moves. Currents driven by tidal heating circulate through the darkness, carrying dissolved salts and minerals, and perhaps, the chemistry of something alive. We do not know. Not yet. But we are closer to knowing than we have ever been. And the spacecraft that will bring the answer is already on its way. All you have to do is close your eyes and drift.